So I'm going to be talking about privacy-preserving payment splitting. And this is joint work with Mihai Christodourescu at Visa Research and Peyman Mohassel at Facebook. So because we've all been at home for a long time now, I wanted to start with a kind of nostalgic photo of having lunch with some colleagues in California Avenue in Palo Alto. And my colleagues in this photo would be happy, but their smiles are all upside down because it's the end of the meal and the bill has come and they need to figure out how to split the bill, and everybody has pulled out their cash and they're moving it around. And this is a very unpleasant situation to be in, all the more unpleasant in our new world where handling cash and touching things is much less enjoyable than it once was. So something that a lot of people turn to get around this hassle of having to deal with the cash is to use payment splitting apps. And if you're not familiar with them, payment splitting apps allow you to form a group of people, and this could be like a group of colleagues that get lunch together, or like a group of roommates or something like this. And then within that group, you're able to make transactions, and the app kind of takes care of splitting the costs among people for you, keeping track of who owes who what and stuff like this. And there are really convenient ways to keep track of costs and debts between groups of friends or colleagues. So the most famous of these that I've used is called Splitwise, but there's kind of a long tail of apps that do this kind of stuff. There's Splitwise, Receipt Ninja, BillPin, SpotMe, Conmigo, SettleUp, the list goes on, and they have many, many users. So this is great from a convenience standpoint, but it's kind of bad from a privacy standpoint for two reasons. One is that now that everything is on the app, everybody in the group sees everybody else's transactions. So you kind of learn a lot about who's getting in debt to who else. But perhaps more importantly, the app is this third party that didn't really need to be a part of your transaction that now learns everything about the transactions that you are making. This isn't great, and it gets even worse when you look at the privacy policies these apps have. So here's something from one of these apps' privacy policies, and they say that they collect, for example, group names, expenses, the payments, and the confirmation numbers, comments, reminders, receipts, notes, memos, anything else, any other information you attach or share while using the app. So they kind of track everything that they possibly could from the app. And other privacy policies are no better. They all collect information that's used to identify you. And this is a rather unfortunate violation of your privacy. So the question we had in this work is it possible for us to get cash-like privacy for payment splitting, where you can kind of have an app that has the same functionality as any app that you might use today for payment splitting, but protects your privacy? And upon hearing this, at least my first reaction as a cryptographer would be to say, well, look, we have a lot of generic solutions in cryptography that enable you to do stuff like this. You could have some kind of homomorphic encryption or MPC where the server kind of facilitates this operation among the group members and doesn't learn anything about people's balances, but then they can all do their transactions. And this is fine. And in fact, the solutions like this have been deployed for various use cases. But the problem is if you try to repurpose existing solutions for the payment splitting scenario, you get performance that isn't so good. And so we kind of have a second goal, and that is that we want to have strong performance and scalability when we're doing privacy-preserving payment splitting. So this is where our solution comes in. So our solution is an Android app that has the same functionality as today's payment splitting apps, but it hides all of the user data about transactions from the service provider. And it runs very fast. So it's a round-based system, like many kind of anonymous systems are. And in each round of computation, the round takes less than 50 milliseconds of computation time on the phone, like on a Pixel phone, and less than 300 microseconds of computation time on the server, which was like a MacBook, for kind of realistic group sizes. And the reason that the performance is so good is because it consists mainly of evaluating AES a few times and addition. So like there's no kind of computationally intensive crypto involved. So when we decided to work on this problem, we started out by doing an informal user survey. And this survey was just kind of an informal thing we wrote down. We sent it out to all of the employees who work for Visa in Palo Alto, and we got 51 responses. And some of the takeaways from this survey, other than the fact that people, when you ask them, at least say that they care about their privacy, is that for people that are using payment splitting apps, the groups that they use tend to be not huge. So this is groups of like 10 people, 20 people, 30 people, It's kind of like your group of colleagues that work with you, so you all go out and get lunch, or like the roommates or something like this, or extended family or the camping trip. That's kind of the size of these groups. And groups only have a few transactions a day. Like, you go and get lunch, there's a few different people get lunch, they charge each other for the bills that they pay, and that's it. And the transaction amounts are usually for fairly small amounts of money. Not that many people are using payment splitting apps to, say, pay their rent. So we kind of took this information, and you'll see how later this comes into the design decisions that we made in building our app. So I want to give you kind of a high-level overview of the architecture. So in our system, the group members connect to the server via an app. And kind of all of the communication for transactions and things is done through the server. So we could imagine, and it might be interesting to look at other architectures where there's kind of some peer-to-peer stuff going on between the phones, but we wanted a drop-in solution that just kind of replaces what apps do today, and apps today connect to the server. So that's what our system is going to do as well. There's going to be a setup phase I'm not going to talk more about, where the group members end the setup phase with a shared secret key. So everybody goes into everyone in the group has some shared group secret that they go into their transactions with. And the operation of the system is going to proceed in a series of rounds, which I mentioned before. And in each round, the users are going to send vectors of encrypted data to the server. And this encrypted data is either going to be an encryption of some real transactions where stuff is going on, or just cover traffic, they're kind of empty transactions. And what the server is going to do is it's going to blindly do some computation over these vectors. It's going to sum up the transactions. It's going to update people's balances. And then it's going to send back to the users their new balances and some information about like who is charging them money, and some additional information that's used for integrity checks to make sure that none of the users nor the server are tampering with the transactions or balances. So before I get into any details, I want to talk a little bit about the security properties that we want to achieve. And I want to focus in particular on privacy, on the privacy properties, although I'll mention the integrity properties as well. So in terms of privacy, there's two things that we want. One is we want to mitigate the privacy loss of the fact that you're now using an app where everybody is in a group and everybody sees everybody's transactions. And the way we're going to do this is we're going to introduce this notion of debtor privacy. And this is that if you're in a transaction and this transaction puts you in debt to someone, we don't want everybody in the group to find out that you're in debt. The other privacy property we want, which is maybe the more natural one, is server privacy. And server privacy is that if you've introduced this server to facilitate transactions, we don't want the server to learn anything about what transactions you're doing. And we formalize this by saying that any two sets of transactions that a particular group could be doing will be indistinguishable to the server. Now, each of these two properties can be achieved kind of independently quite easily. So for debtor privacy, you could actually just take any app right now and have it hide information about transactions from users. So it just kind of says this person initiated a transaction, and it doesn't say who they charged the money from. Debtor privacy would be done. Server privacy, on the other hand, you could achieve easily by having the server kind of act as just a message carrier between the users. And so users would just kind of encrypt and sign all their transactions, send them to each other through the server. And there might be some performance things that could be worked on there, but you'd get the server privacy that you would want as well. The question is, how do you combine these two things so that the server is doing kind of meaningful processing and hiding, like protecting user privacy from each other, while at the same time, the user's privacy is protected against the server. So this is kind of the privacy issue that we want to solve in this work. We also want to handle integrity. I'm not going to talk more about our integrity mechanisms. You can look in the paper for that, but I want to mention our integrity goals. And this is that we want user integrity such that no user is able to create or destroy money and take advantage of the fact that the server can't see what's going on to enrich themselves. And we also don't want a user to be able to frame another user for making a charge. And if the user attempts this, they should be caught. We also want integrity against a malicious server, so that such that the only attack a server can pull off is denial of service. So there's kind of the trivial attack where the server just stops responding to requests, and we can't do anything to stop this. But we want to make sure this is the only thing a server can do. The server shouldn't be able to, say, tamper with user balances or modify transactions in progress. There are a couple of limitations I want to be upfront about. And kind of the most important of these is that we don't hide group membership from the server. So what we provide is that you announce to the server, okay, this is my group of people, and this is the group. And the server learns nothing about the transactions that happen within the group. but it does learn who the membership of the group is. We also don't protect against collusion between a malicious user and server. This isn't a huge problem for the setting where there's kind of some big corporation that's providing an app and then you and your friends make a group. The place where this might come up is if you want to run a self-hosted version of the app. Our solution won't work for this because if you are the server and you're also a user, the security properties are going to break down. So it might be actually interesting to find a way to build a version of this system that does protect against this kind of collusion. So this is kind of the security properties that we provide. Now I want to get into the guts of how the system works. I'm going to present kind of the bare bones version of our core protocol. So the main feature that our protocol needs to support is the ability to make a request. And when I say make a request, I mean you need to be able to charge somebody for some transaction. And it turns out that kind of any other feature you would want, like rejecting an inappropriate charge, is something you can build on top of making a request. Like you can make a request in the opposite direction or something like this. So once you figure out how to make a request, you can use kind of application logic to build out all the other features like bill splitting that existing payment splitting apps do. So in our setting here, we're going to have a group of 4 people, and the first 2 are Alice and Bob. And in this example, Alice is going to request $1 from Bob in their friend group. I'm going to pretend for now that all transactions are $1, and I'll show how we can change that later. So Alice wants to request $1 from Bob, charge Bob $1. What's Alice going to do? Well, I mentioned that each user is sending an encrypted vector to the server. So what Alice is going to do in her vector is she's going to set it to all zeros, except for a 1 in the position in the vector that corresponds to Bob. All the other users who are not making charges, they will put their vector zeros everywhere, except for a 1 in the position corresponding to themselves. So everybody sends up a weight 1 vector, and you set your own entry to 1 if you're not doing anything. You set somebody else's entry to 1 if you're charging that person. And each user is going to encrypt his or her vector and send the result to the server. But for now, I'm not going to talk about the details of the encryption. We'll get to that later. We'll start by showing what the protocol would look like with no encryption, if the server is just kind of computing on this data in the plane. So what's the server going to do? The server is going to add up everybody's values. So it takes all of these rows, adds them up, and then it subtracts 1 from each column. The result of this is that anybody that put a 1 in their own entry, that gets canceled out by the -1, and they end up with a 0. And somebody who put a 1 in another person's column is going to result in their entry being -1, and the person they're charging's entry being a 1. And so what the server is going to do is it's going to take this like sum vector, and it's going to add it into the balances that it's holding for the different users. And the result is that there's -1 in Alice's balance and a +1 in Bob's balance. And the server is kind of tracking debt. So negative here means less debt. So Alice is kind of 1 less in debt to the group. Bob is 1 more in debt to the group. So that's the core of how you make a request, but there's kind of an important piece missing here. And this is, how does Bob know that it was Alice who charged him? And this is really important because first of all, if your balance is just disappearing and you don't know why, that's frustrating. But also, if somebody like charges you money and it was a mistake, you need to be able to reject that charge. And you can't do that unless you know who you charged back. So we need to be able to trace charges to see who created the charge. And the way that we're going to handle this is that for each user, the server is going to take the input in that user's entry of their vector. So it would be a 0 for Alice and a 1 for everybody else in our example. And the server is just going to subtract 1 from that. So you get a -1 for Alice, you get a 0 for everybody else. And then that value is going to be multiplied by a power of 2 that is assigned to each user. So Alice could be 1, Bob could be 2, and so on. And then that product is going to be 0 for anybody who didn't do any transaction. And it'll be the corresponding power of 2 for anyone who did do the transaction. So in this case, the sum of all those values is going to be -1, which uniquely identifies Alice as the person charging. We use these powers of 2 because, as you can see in the second example, suppose Alice and Dave decide to do a transaction at the same time, then because they each have like a unique power of 2, when you add them up, you get a value that uniquely identifies the people making transactions. So here you would have Alice and Dave being uniquely identified by the value -9. Of course, the situation where 2 people are charging at once is a bit of an issue because you, as someone who's been charged, don't know which person charged you. And our solution for this is that when this happens, there's a collision, the clients all realize there's been a collision, and they use the next round to roll back the transactions and then repeat them one by one, kind of in alphabetical order or something. And this means that if there's a collision, you kind of have to do extra work. But the point is that in our survey, we saw that there's only a few transactions happening in a group every day. So we thought it would be fine because these collisions are pretty uncommon. And if they happen, you can do extra work. But in the common case, where there aren't that many transactions, there won't be that many collisions, and we get a performance benefit there. So that's how tracing charges will work. And I want to point out that at this point, we've described a system, even without any encryption, that provides the property we described of debtor privacy. In particular, you see who was charging, but you never learn who was indebted by any transaction. So debtor privacy is something that kind of holds without any need for encryption in this system. Now, the tricky part is how can we combine this with the server privacy? And that's what we're going to see next. So I didn't say what kind of encryption is going to be used, and it turns out we're not quite going to use encryption. The idea is that to add server privacy, the first thing to observe is that the server does the same fixed set of additions every round. So all the operations I described are kind of data oblivious. Nothing is data dependent. The second observation is that all the clients share this group secret key K. So whenever they want to evaluate some PRF or they want to evaluate AES on something, they can all get the same outputs. And it's going to be looking random to the server. So the solution we have for adding server privacy is that instead of actually encrypting the values that they send to the server, the users are going to mask the values with the output of a PRF. So they're going to evaluate AES with their shared key on some information that kind of identifies the group and the user and the round and which entry. And they use this masking and send the stuff to the server. To the server, everything now looks pseudo-random, and it does the same computation it would have done before. But when the users get the values back from the server, they can go back and calculate all of these masks and retroactively remove them from the server's responses. And this clearly depends on the number of users in the group, and it's in fact quadratic on the number of users in the group. But this is another place where we saw in our survey, groups don't tend to be very big. So because this calculation and removing of masks just requires AES in addition, it's very fast. And for realistic group sizes, it's very, very efficient as well. So this is how we're going to add server privacy. And I won't have time to talk about integrity and a bunch of other features that we add on top of this in our paper. So I encourage you to look in the paper to see the details of the scheme. But one thing I do want to talk about is I kind of assumed here that every transaction was for $1. But if you want to, like, say, do a $50 transaction, you would have to do 50 rounds. And this appears to be quite costly. So I want to briefly mention how we can improve this. And the way we're going to do larger transactions is by assigning to each round a power of 2. So the first round is for 1 cent, the second round is for 2 cents, the next one is for 4 cents, and so on. And that means that to kind of transact with X dollars, you need log X rounds. And we can even kind of get a constant improvement by packing a few different transactions into one round. And you can see on the graph, this kind of dramatically reduces the number of rounds you need to do a transaction. For a transaction of $1,000 in our final scheme, we can do this in about 3 rounds. So you can see the paper for details on that. I want to talk a tiny bit about our performance. So on the client side, each round is, and this is a client running on a Google Pixel phone, each round is going to take less than 50 milliseconds for groups of up to like 25 members, which in our survey was 92% of groups. And the overhead for security against a malicious server, and I didn't talk about how we achieve this, but the overhead is super tiny. It's never more than about 20 milliseconds. And the reason for this, as I mentioned before, is that the client is only computing AES and additions. And the bandwidth costs, much like the computation costs, are quite low, especially for groups that are kind of small, which is what most groups are. On the server side, the performance is even better. The server takes about 300 microseconds to do the computation for one group, for a group of 25 people. And there's actually no change on the server side to go from semi-honest to malicious security. So you can get security against a malicious server without actually changing the work that the server has to do. And the server is really just computing additions and multiplications. So the server's performance memory requirements are quite small. And you can look in the paper for more details on the evaluation, including a comparison to one of the kind of generic solutions that I described at the beginning of the talk. So to wrap up, our system allows payment splitting groups to hide information about who's paying, who's paid, how much money is spent, when transactions are made, and more from a potentially malicious server at minimal performance cost. I'd happy to talk more about the paper, so feel free to contact me at saba@cs.stanford.edu if you have any questions.